Okay, so welcome back. So last lecture was about introducing you to various kinds of defects. Now we move on to one particular type of defect. Let us start with the 0 dimension point defects. And what is the simplest point defect that we can have? It is the vacancy or the mono vacancy. So to begin with, let us ask the question, what are point defects? Okay, so I said discontinuity in crystalline system is defect, but what is point defect? How would you define point defect? So point defect is defined as imperfect point like region in crystal. So it is very much like a point which extends up to approximately 1 to 2 atomic diameter. So in a crystalline material you would be seeing some defect which is extending only 1 to 2 atomic diameter, then you can call it point defect, because point, if you go by mathematical definition, it has no dimension and therefore it should be it should not exist at all for that matter. But in terms of this subject, we define point defects when they are extending to 1 to 2 atomic diameter. However, it may be just point a very small dimension 1 to 2 atomic diameter. However, their distortion field and their effect stresses and forces can be felt up to a very large extent. So that is something that we must keep in mind, that defects are not very localized, they always have effect on a very broad or larger scale. Next, we need to understand how these defects are generated. Now, there can be equilibrium processes or there can be non-equilibrium process. Equilibrium processes are simple, like slow heating. If you start a material which is already at equilibrium with equilibrium concentration of point defects, and if you keep heating it at a very slow rate, then with increase in temperature there will be some generation of point defects which will be at equilibrium with that temperature. However, there are other non-equilibrium processes which lead to generation of point defects, and the point defects may not be in thermal equilibrium, meaning that is the density of the defects may not be equal to what is expected, it may be higher or lower. In such cases, most of the time it will be higher. So what are these methods? For example, crystal growth. Growing interface does not have to produce equilibrium amount of defects. So for example, you are growing a crystal, let us say in a single crystal method or a polycrystal method. Now there will be a liquid solid interface. Now that interface does not have to produce that equilibrium amount of defects. It can produce more than that, it can produce less than that. Most of the time, like I said, it is higher temperature, so it will produce higher number of defects, and therefore this will also lead to point defects. Quenching. So you are, let us say, at a higher temperature, obviously if because of higher kinetics or higher mobility, the defects may, whatever the larger fraction of defects that are supposed to exist at that temperature would be generated and they will attain equilibrium. So there will be large fraction of defects. Now you suddenly cool it. Now the defects do not have enough mobility to anneal out, and therefore all those defects have been quenched in. So they will remain in the material. Plastic deformation. When you do plastic deformation, there will be dislocation climbs, and whenever dislocations climb, they leave behind vacancies. So this is again generation of point defects. And when we are doing plastic deformation, we have dislocation density of the order of 10 to the power 14 per meter square. The unit is per meter square, because as you remember from the descriptors, dislocations have length per unit volume. So it will boil down to per meter square. So it is of the order of 10 to the power 14 per meter square. Now these defects can also be generated because of irradiation of electrons, irradiation of ions, irradiation of neutrons. For example, in atomic reactors, they produce very large number of point defects. In fact, irradiation with neutrons leads to increase in volume. So that is one place where you can actually see change in density because of presence of point defects. Another source for generation of point defects is oxidation of silicon. So, whenever oxidation of silicon takes place, then some amount of silicon gets injected into interstitial sites. Similarly, whenever nitridation of silicon takes place, then some amount of silicon vacancies are injected. So, all these are processes by which defects are generated. To begin with, in order to understand to extend our course, we will start with one of the simplest point defects. And what is one of the simplest point defects? Let us say we are in a single pure material, and to be even simpler we will talk about metals, then we are talking about vacancies. And even vacancies can be mono vacancies, di vacancies, there can be cluster vacancies, but we will not get up to begin with, we will just start with mono vacancies. So, we are talking about unit point defects or unit missing atoms, which are mono vacancies. So, now let us look at, to begin with, what we will do is we will try to understand what is the enthalpy of formation. So, let us say it is given that the enthalpy or the Gibbs free energy of formation. So, I will say subscript F is the superscript is 1 V to denote 1 vacancy minus T S again F. So, this is entropy. Now, this entropy, you must be careful, this is entropy of formation. Now, later on we will deal with entropy of mixing. So, this is not the same entropy we are talking about, this is entropy of formation and this is usually 0. To begin with, and again to make it simpler, our calculation will take this as 0, and this is not entropy of mixing. Now, our next step is that since there is energy reduction with the formation of a vacancy, so there will be more and more vacancies getting formed. So, what is that equilibrium concentration? Because as you keep increasing the vacancy, there will be change in the entropy of the overall system. Where is that change in the entropy? Because when you do the mixing, then there is a configurational entropy, or how many ways you can mix, it reduces the overall energy of the system. So, that way the total energy reduces, and but at the same time the H factor, the H term keeps increasing. So, there would be a, you can say, counterbalance to H by this entropy term, and therefore, there will be a minima in the G, which is what we want to find, at what fraction of vacancies in the system that minima occurs. So, let us say that as a result, what we need to find is to find equilibrium vacancy concentration. So, what we need to do is find change in G as a result of, so let us define some numbers, as a result of mixing n vacancies. So, we want this is a unknown number n into a crystal with n lattice sites. Okay, so, what we are assuming here is that there is a system where there are n lattice sites and we will be introducing n number of vacancies into it. Now, what will be the change in this? So, this change can be denoted by delta G, which will be G n minus G naught. So, G naught is when you have 0 vacancies, n is when you have n number of vacancies. And since you have since you are mixing it in the lattice sites, the vacancies are being mixed in the lattice sites. So, this can be related as delta H formation n. Here I am putting the superscript n, meaning this is the formation enthalpy of formation for n number of vacancies, and this time the delta S that I am using is the delta S mix. So, let us call it equation 1 for the time being. So, this is the change in delta G. Approximately what we are saying is that something like this will occur, where delta HF is increasing like this, and we are assuming that the delta S, which is the entropy, is leading to the lowering because there is a minus term over there. So, this is minus T delta S mix, and as the sum of these two, the delta G is varying like this. So, somewhere delta G is minimum, and so here let us define this is fraction of vacancies. So, let us call it x V, and this is energy, which can be Gibbs free energy, enthalpy energy or anything. So, this is delta G, minus T delta S is also in the energy units. So, all these are energy, and one is increasing, the other is decreasing, and because of that there will be a counterbalancing act on the delta G, and we should get some minima, is what we are saying. Now, here again let me clarify what we have said earlier, that it is n is equal to number of atom sites, n is equal to number of vacancies. Now, if we are already incorporating, let us say in the final state the number of vacancies have been incorporated, therefore, n plus n would be the total number of sites. So, now this is another quantity that we have to remember, which is n plus n. Now, like I said, this reaction, which is equation 1, will proceed until delta G is less than 0. Delta G meaning change in the, so here we are talking about del delta G by del n. So, this will keep on we can keep adding vacancies as long as delta G, change in the delta G with respect to n is less than 0. Now, for that what we need to find here is what will be delta HFN. We have already defined delta HF 1V, but we do not know yet what will be delta HFN. For that we can take an approximation that delta HFN is nothing but n 1V. So, the change in enthalpy in the formation of n number of vacancies is equal to change in the enthalpy of one vacancy times n vacancies. So, since we had n vacancies, this becomes n times HF. Actually, it should be n delta HF, but since we have already we are talking with respect to initial and final. So, this will become delta HF, but for the sake of simplicity we will let it be as it is right now. Next, what we need to find is this term T delta S. Now, this is delta S mix. What is delta S mix? According to statistical thermodynamics, this configurational entropy, which is also called, which is the other name for mixing, this configurational entropy, which is delta, which is also delta S mix equal to delta S configurational, originates from many possibilities of arranging these vacancies. So, now let us take an example of just 0 vacancy. How many ways can 0 vacancies be distributed or arranged in a n lattice system? So, that will be only one. Okay. So, in that case it would mean that delta x is equal to 0, that we will see. So, let us say now, so what is this statistical thermodynamics saying, that according to this statistical thermodynamics, configurational entropy originates from many possibilities of arranging vacancies amongst sites. Okay. So, now let us move on to what will be the definition of this S configuration, which is also the S mix. Then according to the Boltzmann rule, this can be given as KB ln W. Now, again this new term is with KB is the Boltzmann constant. So, this is from Boltzmann law. So, now again a new term is being defined. So, we started with the understanding delta S mix, but now we have come up with another term which is W. What is this W? This W is thermodynamic probability which represents number of different ways of distributing n vacancies. Of distributing n vacancies at n plus n sites. And again this is a simple combinatrix, and if you have n vacancies and n plus n sites, it can be easily shown that this W is equal to n plus n factorial divided by n factorial divided by small n factorial. So, now we have this W, but now this W is which was earlier unknown, but the way it has been defined, now we are able to find a relation for it, find a value for it. So, if we find value for it, we already know Boltzmann constant, so we will be able to find entropy. So, the change in entropy, which is from the state where there is no vacancy to the state where there is a vacancy, will be given like this: KB ln W n minus KB ln W 0. What is this W 0? W 0 is number of ways of arranging 0 vacancies. Even if we talked about 1 vacancy, it would become lot more ways, but we are talking about 0 vacancies. So, now just imagine that there is a perfect crystal and you want to add 0 vacancy, meaning no vacancy into it, meaning the overall site remains as it is. So, there is only one way, and therefore, this W naught becomes equal to 1, and therefore, this ln W naught becomes equal to 0, ln 1 is equal to 0. Therefore, delta S configuration is now defined as ln W n. Now, we need to find this ln W n, which is already given here. So, it is KB ln n plus n factorial by n factorial by small n factorial. So, this is our delta S configuration. So, now we have seen that to find what is the change in the energy with respect to adding of vacancies, there are two terms, delta H formation, which we have for n vacancies, which we have equated as n times delta H formation of one vacancy, and the other term, which was the entropy term, we have now defined it in these terms. So, now we have both the relations. So, now we should be in a position to simplify it. Okay. So, because what we have right now is delta S configuration in a factorial term log, inside the log we have a factorial term, and for this the well known Stirling approximation is used. So, using Stirling what is this Stirling approximation? This is ln times x factorial is equal to x ln x minus x. This is true only when x is much greater than 1, much larger than 1, and therefore, our relation which said that delta S configuration is equal to KB ln and you can say this is the denominator can be put as negative of log. So, minus ln n factorial, the uppercase n and then also the smaller case n. So, now we will have to apply this Stirling approximation on all the 3 terms, and it is not very difficult, it will become something like this. Minus, so this is for now for the second term, we will expand the second term using Stirling approximation. Minus of minus becomes plus, therefore, delta S configuration is equal to KB. Now, we will put the terms with log in one place. So, this is the full form of delta S configuration which can be easily evaluated. Now, we do not have any factorials over here. In fact, now with what we have, we can even simplify it further. For example, as you can see that this n plus n over here, number of vacancies would always be very smaller compared to number of atomic sites. So, therefore, this will quantity n plus n by n, this can be approximated as n, because n is much smaller than n. Now, here n plus n can be approximated as n, and therefore, this is since ln 1 this becomes 0. So, we have only 2 terms n KB ln, and if we reverse this, why we will reverse this is I will tell you in a moment, is n by n. Now, why did we reverse it? Because this quantity, this represents nothing but fraction of vacancies. So, this becomes minus n KB ln x 1v or v, what I think we have used earlier v. So, I will put it as v, and what is this xv? This is fraction of mono vacancies. It is important to keep this word mono vacancies, mono, because we will see that similarly you can also calculate for di vacancies or tri vacancies or higher fractions or higher orders, and simultaneously you would be able to show that their fractions are much smaller. So, now this is the relation, and if you put delta G will be equal to delta N delta H formation 1V plus, now because this is minus term, so this will become T, although this quantity itself will be negative. So, this term will itself still remain negative, and this becomes N T KB ln x v. Actually, let me use this 1 v in all these places, because to differentiate it with respect to mono vacancies. Now, earlier we have when we were deriving these relations. Okay, now let me go to the next page. So, let me write it again here, the relation. Now, earlier when we were deriving, if you remember, we said that the S or the delta S, if we are looking with respect to difference, delta S formation is approximately 0. Now, if we do not ignore that, then we will have some more terms over here. So, we will have another delta SF coming over here, but before that let us get to what we need here. What we want to what we started with was to find out what is the concentration of X1V, right. Now, when we have what we said, that when you keep increasing the concentration of mono vacancies, there will come a point where the energy will not reduce any further, which means this will become 0 or something like this. You will get a relation that we will derive next time. We will get a relation something like this. And this n by n is nothing but our fraction of single mono vacancies. This will be given by and like I said that if you had not ignored the SF delta SF formation term, then this would be further accurately represented by this relation. So, this is a approximation. This is more accurate, because here we are not ignoring so this we have using this derivation, we have been able to obtain the value of the fraction of mono vacancies. So, this is the relation that gives it, and next time what we will do is try to understand what is the effect of addition of these mono vacancies on delta G. How does delta G and delta S change when we keep increasing mono vacancies, particularly when in the initial period when we have almost no vacancies to small number of vacancies. So, we will end here and we will come back and extend what we understood today. Thanks.